Boom. What's the 20th? Ooh. I am going to tell you what today's notes are called, and you are going to have no idea what I'm talking about. If you were to Google this, you would find a very confusing definition. Um, you could read it several times and still probably say, "Yep, don't know what's going on here." So as I always do, I consider myself somewhat of a translator. I think it's part of what I get paid to do is take things in math that are officially very like people try to make them look so complex, but my job, I think, is to try to translate things down to in a language that people can understand. So again, if you Google this, you'll see all sorts of weird stuff. You'll also see it called the rational zero theorem. There might be other names for it as well. So we're going to transition for a while. You're going to see or hear um, that when we're finding zeros, I want you to know that we're also finding roots. And so today, because most people call it the rational root theorem, I thought I'd get that out into your vernacular that it's also where when we find roots, we are finding zeros. So it's the rational zero theorem or the rational root theorem. But you might hear me start to use the word root. Know that when I say that, I'm talking about what we've been doing, finding the zeros. Zeros and roots are effectively the same thing. I believe that, like contextually, there's a different time to use each one. I believe root refers more specifically to the solution of an equation, whereas zero is more from like a graphical perspective. But they're somewhat like interchangeable as far as practical day-to-day stuff goes. So here's your first math problem. I'm going to give you a function, and I'm going to say to find all the roots or the zeros. What's missing? Pretend if you took the quiz on Thursday, or even if you didn't, pretend that this is what we just got done doing. If I said ready, set, go, what's missing? The freebie, right? There is no freebie. And that's where the rational root theorem now pops in. So I wanted you to appreciate for a week or so what it feels like when someone gives you that foot in the door. Like if I said f of 5 equals 0, then you could use 5, chip it down to a quadratic, and then you guys are powerful. You can solve any quadratic in the world, literally any quadratic. With the quadratic formula, you will never miss. But what changes today is that rather than giving you that free one, we've got nothing at all. Okay. So the rational root theorem, I'm not going to give you some definition of it. If you look it up again online, you're going to see P's and Q's. I'm going to try to keep this as simple as I can. What you're going to do is you're going to take and you're going to make a list of all of the factors of the yellow number, and you're going to take and make a list of all of the factors of the green number. And you'll notice there is no box in the green box or no number in the green box. What would be there? Good. So I wanted to start you out with this one just because it's the simplest thing that can happen with the rational root theorem is that if the green number is 1, what happens when you put something over 1? When you make a fraction with 1 as the bottom? It's just that same whole number, right? So I wanted to start us out with this one, a nice little friendly introduction into this that we're not going to have to worry about fractions yet, not on this problem. So what we're going to do is we're going to take all of the factors of the yellow, and we're going to take all of the factors of the green, and we're going to build every possible rational value. And remember, rationals can be whole numbers or integers, like -6 is rational. 2/3 is rational. Anything that can be expressed as a fraction, like without roots, is a rational number. So if we make a list, a comprehensive list of every possible factor of the yellow number and every possible factor of the green number, and we build them as fractions, we will have a list of every possible freebie. What you're used to seeing from me when I give you the freebie and I say f of 4 equals 0 or f of 2/3 equals 0, your job starting today now becomes to find that first one on your own. That's where the rational root theorem comes in. Okay. So having said that, you got to be good with your basic math. Let's start with the factors of 40, because 40 is the yellow number. And notice I did not include the negative, and I'll talk to you about why in just a second. Okay, so you don't need to consider him as a negative 40. He's just a 40 for now, for our purposes. What are the factors of 40? And if you could give them to me in order, that would be great. Yeah, small to big would be better. Oh. What's the first factor of 40? 4. Nope. Nope. 1. Thank you. Don't overlook 1. Okay, 1 is the first factor of anything, right? What's the next factor of 40? 2 is a factor of 40. Next. 4. I agree. We skip 3 because 3 doesn't go in nicely. Next. 5 does go in. Next. 8. And at this point, if you remember this from grade school, your teachers probably taught you to build bridges or rainbows or something. I don't know what thing they used, but once you find two numbers that make your target 40, then you could just build bridges now. And you can rest assured that you don't have to now check every number. You can now build them. That's provided that you've not skipped any on the way uphill, right? So who can I bridge with 4? Because 5 and 8 bridge. Do you see how they make 40? So 4 bridges with 10. Who does 2 bridge with? And who does 1 bridge with? If you're successful in your first half, you never have to sit and scan all the numbers. They say once you build 1 bridge, then you can connect all the others. It's a big time saver. And what are all the factors of 1? 1. 1. So when we build fractions out of all of these, this task becomes a bit more taxing when there's a number on the bottom that isn't 1, but the 1 becomes pointless in this case. So like, for example, if I take the first number on the yellow list and divide it by the first number on the green list, I get a number called 1. So I'm going to put 1, and then I'm going to put a positive and negative in front of it. What this means is that positive and negative 1 are both what you're going to hear me call a lot candidates. I don't know if 1 is a root. I don't know if negative 1 is a root, but I know that they're both potential rational roots. See, the ones we're not going to find ever by sitting here staring at it, and I mean ever, are like 5 plus or minus 3 root 2 over 6. Like, no, you cannot look at it. And I mean, maybe there's someone in the world with that ability. I have no idea, but we'll never find those in a million years. But the rational roots are our foot in the door. And that's why the rational root theorem is so huge, is he's giving us a list of candidates that we can use to chip that layer off to get it down to a quadratic. Who's the next number on my list? 2. And again, what I'm doing is I'm building fractions. This whole process will make more sense, I think, on example 2 when there's a non-1 on the bottom, I hope. After that, positive, negative 4 after that. How many candidates do we have right now in our notes? I heard someone, I think, say it, 8. Yes, 1, negative 1, 2, negative 2, 4, negative 4, 5, negative 5. Those are all candidates. After that, positive, negative 8, positive, negative 10, positive, negative 20, and positive, negative 40. This is a pretty average size list. You'll see some lists that are longer than this. You'll see some lists that are shorter than this. If the back number had been like a 9, then clearly we'd only have 6 candidates, right? Positive, negative 1, positive, negative 3, positive, negative 9. So the less prime the numbers are, the more of a pain this is going to be. So that's what the rational root theorem states, is that if there are rational roots, and by the way, every problem I give you for the next week or few days or however long we do this, every problem I give you will have at least one rational root. So I'm not going to send you on a wild goose chase. Will there be instances in your math career much later on where you maybe try every rational root only to realize that they don't work? I suppose that, yes. And in that case, then you just bust out the bigger guns. So for now, what I'm saying to you is we now have to try these until we get lucky. And this is where divide and conquer is usually a pretty, I don't think that's the right use of that expression, but the in this case, we're maybe, what we'll find when we get good at this is Landon might try this and Riley might try that and Allie's trying this and Fergie's trying this. And so eventually, like, especially when you're working on our homework assignments, if you're working with some friends, you guys should divvy the task provided that you're working with someone that you trust and that they're not going to mess it up. Because if they try a number that works, but their math leads to the conclusion that it doesn't, then you're all probably going to get upset. So make sure that you trust the people to whom you delegate the tasks. So we're going to do now our rational or our synthetic division, just like we always have with the numbers that are at the top of the screen. So we're going to set up a template. I find myself, I use pen a lot when I do this because once I build the template, I'm going to be erasing a lot. And so it helps to not worry ever about erasing the permanent numbers because these ones now, the 1, the -9, the 28, and the -40 are going to be a permanent fixture now in your life for the next few minutes. Okay. So I say what you'll find that groove, but using a pen for those is a good idea. Just then you don't have to worry about erasing a negative or something like that. And we begin. And for the first time ever, we have no number to try because we know it works. We're going blindly into this. And you can be as you can develop your own system, your own method of organizing, whatever. But what do you want to try first? 5 works for me, Parker. So Parker has elected to just dive right into the center of the set and just try 5. And if 5 works, then we can all thank Parker. And if it doesn't work, then that's okay. At least we have 1 now out of our 16 that we don't have to try again. So we're hoping for a 0 down here. If we hit a 0, then we know we found the rational root. And so we're going to drop the 1. 5 times 1 is 5, -4, -28, and in a 1 out of 16 chance. I don't know in my teaching career, Parker, that has ever actually happened. But good job. That will oftentimes, and honestly, I didn't even remember what it was because I didn't write it down on my note card. Um, so, I mean, there will be times when you find that on your, I'm sorry, you're like your 12th try. But you want to be good at synthetic substitution, right? Like you don't want, and I did see on the quiz that there are rinky-dink mistakes that happen in there. And I can't, I don't know what to tell you other than just don't do that. Like at this point now, we can't afford little mistakes because you might be on the rational root. Oh, it's heartbreaking. And then you miss it. And then you spend 15 minutes trying all the other ones only to realize that you had it. You were at the doorstep and you blew it. So try not to make any errors. Nice find there, Parker. Was that just a random guess? Had you tried it?
Well, not really.
You just
You get 8 from -20.
you just you felt it? Man, that's impressive. All right. Parker might become our go-to guy for the next 15 minutes here. So great job. Anyways, now that's going to take us to the ending that we're pretty familiar with. So had this been a normal problem like last week, I would have given you f of 5 equals 0 or x minus 5 is a factor, but I didn't. Parker found it for us, and we're down to x squared minus 4x plus 8. Is that factorable? No, not even close, right? Yeah, x minus 2, x minus 4 would be maybe the only candidates, and they sure don't add to make -4. So we're going to dive in and use our quadratic formula where a is 1, b is -4, c is 8. And you should be pretty good at this by now. What does x equal? X equals 4 plus or minus the square root of 16 minus 4 double blank all over what?
1.
Nope. 2. And in the blanks, we're going to put the A and C values, which are 1 and 8. These are going to be real, rational, or imaginary. Definitely imaginary, because the 3 numbers at the end will produce something larger than 16. What do the three numbers at the back make? The 418? 32. So this is 16 minus 32, which is negative 16. So we're currently looking at x equals 4 plus or minus the square root of negative 16 all divided by 2. Tell me about that root. It's
not-
I know what you mean. It's imaginary perfect. Again, you're 2 for 2 on things that I don't think anyone's ever said before. Imaginary perfect is a pretty dope way to say that. So this is now going to morph into x equals 4 plus or minus 4i over 2, and the Dorito is in effect. Remember, the Dorito only works if all three parts agree. You cannot partial Dorito. I mean, that's a lie. You could if you know how to do it the other way, but generally we just would say leave it alone unless you can go the three-headed monster. These can all be divided by 2. And if you divide them all by 2, you're left with a 2 and a 2 and a 1. So what's my final answer? Correct. And then we're going to put a comma. And in the past, I would have said, don't forget your freebie. But this time, you generated this all on your own. What is the third solution? 5. It's the one Parker found for us, right? So there are your solutions. And we did that all by ourselves. We had no assistance from anybody. We found all the zeros just using mathematical awesomeness, okay? You ready for round 2? Nice job, Parker. Thanks for the help. That could have taken a lot longer. Next one is going to be a function, and it is going to be 4x cubed minus 9x squared plus 6x minus 1. And the order is key. Math is a nuancy little thing. Like people sometimes overlook the importance of what we perceive to be small details. It's important. Yellow has got to go on top. Green has got to go on bottom. What are all of the factors of the yellow number? 1. What are all the factors of the green number? 1, 2, and 4. And your job now is to build every possible rational value using the yellows and the greens in tandem. But again, we're getting help here. The last one will be the hardest. The fourth one will be the hardest. We're getting help here from the fact that one of them is a 1, which eliminates possibility of like tons and tons of things. So what's the first possible candidate? Positive, negative, what? 1 over 1 is 1. What's the second possible candidate? 1/2. It has to go in the right order. Remember, yellow over green makes 1 over 2. And then what's the last possible rational candidate? Positive, negative, 1/4. How many candidates total then do we have? 6. Make sure you're aware of the fact that those positive, negative signs are not unimportant. They need to be there. So the positive and negative version of every candidate has got to be considered. Okay. Every problem you do for the next few days, this will be an expectation. This is not up for debate. It's not up for negotiation. It's a huge part of everything now we do is to make a list. The instructions will usually say make a list of all possible rational zeros or roots. That's important that you do that. Box it up if you want to, but that's a very prized possession. And now it's time to build our template with the permanent numbers. So our permanent numbers are 4, -9, 6, and -1. And Parker wants to try +1. So just
With like with 1.
it just becomes unimportant because of the fact that the rational root theorem states that we have the positive and negative possibility of every one anyways. So the signs in the original polynomial are irrelevant. Yeah. Good question. All right, let's do this. Let's test, see if Parker goes 2 for 2 on the day. Did he get it? Is he 2 for 2? All right, I'm starting to get a little freaked out by Parker here. So 1 times 4 is 4. Add those, -5, multiply -5, 1. Yeah, you're freaking me out now, Parker. So the first one, you took a 1 in 16 shot and hit it. And this one, you took a 1 in 6 shot and hit it. I don't know how familiar you guys are with probability, but for something to happen that has a 1 in 16 chance, followed up by something that has a 1 in 6 chance, your probability of that is 1 out of 96. So Parker has performed a almost 1% feat here. Congratulations there, son. Yeah, I can't explain it. I'm going to be freaked out if this happens again, fifth hour. That 5 was a stab. Just, yeah, I'm still bothered by that. So we're down again. He did it. Parker to the rescue. Parker saving us time in our notes. So is it factorable?
Yeah.
I would say that it is. If I take the number in front and I multiply it by the number in back, I get 4. Are there numbers that multiply to make 4 and add to make -5? -1 and -4, I believe, foot the bill. Having said that, then we don't need the quadratic formula. If you love the quadratic formula, you go do that little thing while we factor. So I'm going to try out these shells here. We know they're both minuses, and we know that it's going to work only if we use ones. The only way this would not work, I mean, excuse me, the only other way it could work would be if we needed the 2 and 2 template, but I believe this works. If you know how to factor, you see that you got your -1x and your -4x presto. So in this case, we have all three rational zeros. So we are going to find our other answers. What answer do we get from the first factor? I couldn't hear you, bud. Correct. +1 divided by 4. What answer or zero or root do we get from that one? X equals 1. And what was the one that Parker, again, black magic got us? 1. So the way we express these answers now, starting today, I'm going to start talking to you now about, I don't bring these things up early because I just think that there's a time and a place for things. Like I didn't want this to be something that we were burdened with before, but because we have the same answer twice, this has what we call multiplicity. So rather than write your answer like this, we're going to write it like this. We're going to say x equals 1/4, comma, x equals 1. And then in a little parenthetical comment, you're going to put ×2. And that becomes our notation from this point on when we show that a root has more than one instance. Okay. So that makes the graph behave a certain way. And I don't know that today's the right day to talk to you about that, but that makes the graph do something at 1 that we'll talk more about when we actually start graphing these polynomial functions, okay? But this is how your answer should be expressed. X equals 1/4 and x equals 1. And the word we use for this, I don't know if you caught me saying it, this word is multiplicity. So when a root occurs more than once, we say that it has multiplicity. And that's the notation. Any questions so far? All right, let's do example 3. This one is a function. Let's call it a different name. Let's call it g of x. I'm getting tired of f of x. He is going to be x cubed plus 64. As I wrote this problem last night, I asked myself, I'm always curious when I write a problem like this as to um, will anyone get crafty with it? If we just go like normal rational root theorem, what is the yellow number in the back? What's the green number in the front? 1. So we're faced again with the situation in which we aren't going to have fractions like the first example. What are all the factors of 64?
2.
Yep. 4, 8. And 8 bridges with himself to make 64. 8 times 8. And so at that point, we have a bridge, which means we can now build all of the subsequent bridges. 4 bridges with what?
16.
Correct. 2 bridges with what?
30.
And 1 bridges with. Good. So in a case like this, you'll get better at being efficient. You realize I probably shouldn't have even written this because honestly, like I am going to do my due diligence to continue the lesson and put it all over one. But if you see over one coming down the pike, then as you're building the yellow list, like you might as well just put your positive negatives on them on the site, right? Like what's the point? But I'm doing it just so I can be thorough. So all of our possible candidates, oh boy, here goes Parker again, are positive negative one, positive negative two, positive negative four, positive negative eight, positive negative 16, and positive negative 32. This, I want to say again, this thing in the white box is 100% an expectation. And it's not the kind of thing where you do it on separate paper and go, oh, I just didn't show it. You have to show that. That's huge. All right, whiz kid.
Mm. Mm.
Well, that is, let's set up our template first. Based on what's up here that I'm underlining in purple, what will my purple numbers be?
Um, zero, zero.
Thank you for that. I'm really glad that you did that. We need those zeros to scaffold our way down to the floor, right? So we have x to the third. There was one of those. There are no x to the seconds. There are no x to the first, but there is the nice job, Landon. So there is the structure. And this one's going to get out of hand in a hurry. You'll see you did say negative 64, right? But this one will probably bail on relatively quickly, I'm thinking. So let's give it a go. Let's dive in. One, multiply those. What do you get? Negative 64. Add those. What do you have? Negative 64. And Parker threw out a quick never mind because he realized that despite his greatest intentions, I have no idea what 64 times 64 is, but it turns out it's positive 4,096. And then if we add those, right, then if I do think your heart was in the right place. I like the way you kind of vibed with the problem there, but now we have 64 times 4,096, which is 262,144, which takes us to 262,208. So I'd say we missed our zero by a little bit. Okay. So you want to try something else? But hey, the good news is that's one less we have to check later. So there we go. What else? You want to try negative four? You nodded your head as if you were a young man who already knew that that works. Good for you, Nick. Yes, negative four will work. And I'll show you in a second how using your prior mad skills, you actually could have cracked this code a lot quicker. But I didn't know if anyone would throw that out or not. And you didn't, so I skipped past it. But yes, this will work. This makes negative four, add negative four, multiply 16, add 16, multiply. Nice build up there to the zero. Just quickly before we finish this problem, listen, it's been a long time since I've asked you this question because, it's almost November. What is that?
Um,
It's a sum of something, but it sure as heck ain't squares. It's a sum of cubes. And earlier this year, we learned that to factor a sum of cubes is something that we can do. What's our A value? X. What's our B value? 4. And if you build a short set, long set off of this, like we did back in the day, it would be x plus 4 times x squared minus 4x plus 16. And if you know math, then you understand that that right there gave us that right there. So in the future, if you see something like a sum or a difference of cubes, you can actually bypass the rational root theorem by using a little bit of basic factoring, which is pretty cool. And look at the numbers, by the way. I mean, this is all math is amazing. Look at that. What number's right there? 1 right there. Negative 4 right there. 16. Look at those. They're right there. So pretty cool stuff. Anyhow, let's finish. Let's do what we came here to do and let's find all the zeros. We have found one. Well, Nick found one. Thank you, Nick. So A is 1, B is negative 4, C is 16. No way are you factoring this sucker. So what does X equal? plus or minus. What goes in the blanks, right? Are these going to be real, rational, or imaginary? Yeah, imaginary again. And the reason for that, if you're lost, is because the numbers in the white box clearly multiply to make, um, did I put 64 there?
Yeah.
Boy, talk about getting ahead of myself. Apologies. I knew already that my brain was already doing the 4 times 16. I apologize for that. We know that the white box is going to make more than 16. So this is going to wind up being 16 minus 64, which is what? Perfect. So, as always is the case with the quadratic formula, we get to this sort of ending um, where we now have to deal with the root and there. So off to the side, and I don't know, it just there comes a point in everyone's math career where you just know what 48 is. Does anyone know quickly off the top of their head how to break down the square root of 48? Do not use 4 and 12. 48 would have been a death number back in Algebra 1 that I told you do not use 4 and 12. There's a better one. If you use 4 and 12, then you're going to have to break down the 12s, and I just don't want to be a part of that. That's the one. And so the more you see these death numbers, the more you just know, rather than reinventing the wheel every time, know going into it what it's going to be. This is going to become 4I root 3, right? So I'm going to sub out the square root of negative 48 and bring this one in, and I'm going to Dorito it. What is the final answer going to be? Mhm. Correct. And then, of course, the one that Nick found for us was x equals negative 4. All right. This is one of those days where I am going to take your whole period because I've only got 8 minutes left. So you know what that means. Tomorrow will be just a full work day for you, but we got to get through this last example. So I don't know why I thought I could teach you the rational root theorem in like 26 minutes. That's just crazy talk. Our last one is, let's do h of x. Why not? And he's going to be 15x cubed plus 8x squared plus 16x plus 3. And again, what doesn't change is the process. We're going to take the yellow number and we're going to make all of his factors. What are the factors of 3? 1 and 3. Those go on top. Factors of the green number. And we're going to now build a list of candidates. And so for the first time now today, I'm going to show you how we do this in an organized way. You want to take, at least I think you should want to be organized about this. You're going to want to take the first number on the top, which is 1, and build every possible fraction using him and each of the guys on the bottom. So at this point, we're just going to dive right in and put positive, negative. Here we go. And the first one is right here where I'm moving my pen. 1 and 1 make 1. What's the second one going to be? It's right here where I'm moving my pen. 1 compare with 3 to make 1/3. The next one is right here where I'm wiggling my pen around. 1 and 5 make positive, negative, 1/5. And the last one is 1 and 15. They make positive and negative 1/15. So 1 has run his course. He's done. We've built every possible pairing using him as the numerator. So he's like, adios, amigo. And now we're on to the 3. What's his first pairing make? It's this one. 3 over 1 makes 3. What's the next one? And I'm not going to write positive, negative 3 over 3, which equals 1. Why not? Because I already have it. So you'll see this in the rational root theorem as you get a lot of redundancy. And if you already have something, don't write it again. That's just silly, right? So 3 over 3 we can omit. What is the next pair right here? 3/5. And the last pair? 3/15, which reduces to 1/5, which again, I already have. So that last comma was unnecessary. And so we get, right? So we're going to make a purple list, 15, 8, 16 and 3. And we're going to get in there. What do you want to try first? How many candidates are there, by the way?
Well,
12. 6 times 2, 6, 6 positive, negative each. All right, I'm leaving it to you. What do you want to try? Let's see if Mr. Kreskin Wizard over here can get it.
one.
Okay, so Parker has said, let's try 1/3. And by the way, you'll generally know with these pretty early on if you're having success or not. The failure will come pretty quickly. So 15, feeling good so far. What's a third of 15? 5. What's 8 plus 5? 13. We should stop now. Why?
Because you can't do three.
Because I'm going to try next to take a third of 13, which is 13 thirds. And I will tell you this from my experience, if you encounter a fraction early, jump ship. All right, don't continue to struggle and torture yourself by working with that. A third times 13, that ain't going to happen. So I'm going to go ahead and abandon that. So what do you want to try now? 1/5. And I will tell you, if this fails, we would be wise to try the negative version of it. And I should have said that last time too, by the way. But in fact, I'd like to go back after this. If this fails, I want to go back and do negative 1/3 because sometimes you have it, but you just need the negative version. So let's try this. 15, a fifth of 15 is 3. 8 plus 3 is 11. Let's jump ship. So let's try the negatives of the ones that we've tried. The first one was a third. Let's try negative 1/3 just to see. And then we'll try negative 1/5. 15. What's that make? This has to be quick. We can't be messing around with this. Yeah, negative 5. A third of 15 is 5 for Pete's sake. And then you subtract and get 3. And then you realize that's another one where it's good to jump ship. Let's try negative 1/3 or negative 1/5, excuse me.
Oh, wait,
Okay. Did we get a 3 there? I'm so sorry. Let me go back. That was negative 1/3. Apologies. Yeah, and here I am lecturing you about not doing stupid things. So that's good. Is it going to work? Negative 5, that's a 3. Um, that's negative 1/3 of 3 is negative 1. And that's going to be 15. And it's nice. It came out nice, but it's not 0, right? I'm really sorry for my mistake. So we didn't get it, but thank you for calling me out on my incompetence. Let's try negative 1/5. Let's drop that 15 down. What's negative 1/5 of 15? Negative 3. 8 and negative 3 make 5. Of negative a fifth of 5 is negative 1. 16 plus negative 1, 15. And a negative a fifth of 15 is negative 3. So we found it. So I appreciated that you guys dug right in, that you didn't chicken poo out and just try one first. Like I did purposely want to make sure that our last one was a fraction. So good job, good instincts on that one. So we found it. It took a little bit of fixing your math teacher and doing, I don't know, 4 or 5, but we got her. And now what are the 3 numbers that we're going to use for our quadratic here? 3x squared plus 1x plus 3. And that is not factorable, right? So to finish our class together here, let's finish the quadratic formula. So our numbers are 3, 1, 3, and here we go. What does x equal? No, negative 1, plus or minus the square root of 1 minus 4 blank blank all over 2 times 3, which is 6. In the blanks, 3 and 3. What is 4 times 3 times 3 in this white box? It's 36. And what is 1 minus 36? Negative 35. So we have x equals negative 1 plus or minus the square root of negative 35. And that you can't do much with the root of 35. All right, it is what it is. But what we can do is get rid of this square root of negative 35 and swap it out with I root 35. Any Dorito in effect here? No. The absence of a number where this yellow arrow is pointing tells us the Dorito is out of play. right? If no one breaks out of jail, then you stop. You're done. And so we're going to say x equals -1 plus or minus I root 35 over 6, comma, what else? X equals -1/5. And boy, talk about taking it right down to the wire. Finish that with, you're welcome, 22 seconds to spare. I will take the assignment off of Canvas because clearly we're not going to work on that tonight. Tomorrow, we're going to work in class.